Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, I'm back after nearly a month on the road, so we are fully live today with no pre-recorded segments. Now, on this channel, we have covered pretty extensively RTD and thermocouple type temperature sensors, but we haven't covered another type of temperature sensor, but we're going to resolve that today. Today's topic is using thermistors with Horner OCS All-in-one Controllers. And to help me introduce today's topic, I'm going to bring in our product manager, Mr. Casey Gardner. How you doing today, Casey?
Hey, I'm doing good. How's it going, Chuck?
It's going terrific. Now, on the subject of temperature sensors, RTDs and thermocouples, they're basically everywhere in industrial applications, and thermistors are a little harder to find. What types of applications utilize thermistors?
Sure. So I think most common that we see is usually in the HVAC industries or building automation. That seems to be where they're most prevalent.
Yeah, that makes sense. There are some limitations to thermistors, and those industries don't really have a problem with those limitations, and we'll cover those during the content today. Now, as somebody who's kind of looking over our product line as an automation user, they will probably notice that there's a lot more products that we offer that support RTDs and thermocouples versus thermistors. Why is that?
I think part of it is just how common it is, and for a lot of these different types of industries. Again, we mentioned some specific markets like the HVAC and building automation, but RTDs and thermocouples just seem to be much more widely used for a lot of other applications, mostly due to maybe limitations for thermistors for that matter.
Yeah, that makes sense. The more widely supported sensors are, the more widely they need to be supported in your product line. Now, that being said, even though our thermistor support's a little limited, I did see on our production schedule or on our development schedule a new thermistor development. Tell us about that.
Sure. So we as you said, we do definitely have some future developments underway. One of which is for our OCS-IO OCS-IO platform. That's going to be something that is new and still evolving, and we'll have a 8-channel thermistor module in the future for that, hopefully 2023.
That sounds good. And 8 channels will be nice, because I know in some applications, building automation, for instance, you might have several temperatures that you're wanting to monitor at once, and an 8-channel module will make that really nice. Okay. Thanks, Casey. Thanks for joining me today. Now, before I let Casey go, I want to remind you, if you're watching this live, we'd love to see your questions in the chat section. If you're watching this on replay, give us your questions and comments in the comment section, and we'll get back to you just as soon as we can. All right. Thanks again, Casey, and let's take a look at today's topic. Okay, we're going to start out by defining what is a thermistor in a little more detail than Casey and I covered in the opening. We'll talk again in a little more detail where thermistors are used. We'll talk specifically about what Horner products support thermistors and which specific thermistors are supported, because unlike RTDs and thermocouples, there's more variation with thermistors than other types of sensors. And we'll have plenty of demonstrations, so if you need to apply a thermistor in your application, you'll have all you need to know. All right, here we go. What is a thermistor? Well, the basics are it's a temperature sensor whose resistance varies with temperature. But wait a minute, that's also the definition of an RTD as well. So let's compare thermistors and RTDs to kind of compare and contrast the similarities, but primarily the differences. So thermistors are made materially of metal oxides or combinations of metals, whereas RTDs are most typically pure metals. Thermistor standards vary by manufacturer, whereas RTDs are more standardized. So if you buy a PT100 RTD from a manufacturer, you can pretty much know that that same PT100 specification purchased from a different manufacturer is going to yield about the same results. That's not always true with thermistors. Another thing about thermistors is their resistance versus temperature curve is exponential, whereas RTDs are much more linear. Also, thermistors have a narrow temperature range, whereas RTDs have a much wider range. And if we add thermocouples into the mix, Thermocouples have the widest range even yet. Okay, so those are some differences between thermistors and RTDs, both sensors whose resistance vary with temperature. Now, there's actually a couple different classifications of thermistors. There are NTC thermistors and PTC thermistors. NTC stands for negative temperature coefficient thermistor. In other words, the resistance falls as the temperature rises. You have an inverse relationship there. Now, these are the sensors that are typically used to measure temperature. But there's also something called a positive temperature coefficient thermistor, where resistance rises as temperature rises, and these are typically used as a fuse. Now, for today's particular topic, we're going to be talking about thermistors, and when we do, we're really talking about NTC temperature sensing thermistors. Now, on the screen there, I'm showing a schematic of one of our Horner I/O modules that supports thermistors. And you can see on the far left there, we're showing an external wiring of a thermistor into the module for measurement purposes. And then, interestingly enough, on the right-hand side of the diagram, you can see in the internal module circuitry a PTC type thermistor that's being used as a fuse. So they're both very commonly used, but from an industrial standpoint, when it comes to temperature measurement, we're talking NTC thermistors. Okay, what are the advantages and disadvantages of thermistors? Well, they're very inexpensive, they're very stable, and they're durable. So those are significant advantages. And as you can imagine, in HVAC type applications and building automation type applications, inexpensiveness is important. And the disadvantages of thermistor, namely the biggest advantage of a very limited temperature range, are not such an issue with building automation because of the fact you're generally measuring ambient type temperatures over a pretty narrow range. Some other disadvantages of thermistors are the fact that they are nonlinear, they're relatively slow, and they're not very well standardized. Again, like I mentioned earlier, you buy a thermistor that on the surface appears to be very similar from two different manufacturers. They could behave quite differently because they have actually different temperature curves. Now let's take a look at that thermistor resistance versus temperature curve that I've got there on the middle of the screen. And you can see that most definitely you're looking at an exponential relationship, not really a linear relationship. Now, the temperature ranges shown here on the screen with the graph are approximately minus 50 degrees Fahrenheit to about 240 degrees Fahrenheit. And there's really a big difference in terms of the resistance. You can see that the resistance goes well up to well over 200K and can be well below 1K at the low end. And then on the right there, I'm showing kind of a segment of the thermistor chart, which is probably one of the more popular temperature ranges, and that's between 50 degrees Fahrenheit and 100 degrees Fahrenheit, because that's kind of the ambient range very commonly used in indoor applications especially. And even in that limited range, you can see there's quite a difference in terms of the resistance. Okay, now more specifically, where are thermistors used? Of course, we've talked building automation, we've talked HVAC, but what we can be talking about are the different areas or the different temperatures that need to be measured in those particular applications. So you could be talking about the temperature in an air duct, the temperature of a room, outdoor air temperature, just ambient air temperature in general, let's say in a warehouse. It could be air temperature in a refrigerator, for instance. And it's not always air. It could also be water temperature of a cooling tower or maybe a swimming pool, whether it's a public pool or something of that nature. So again, you can see these most common applications are certainly building automation and HVAC type related. Okay, now let's talk about the specific Horner products which support thermistors, starting with the Smart Block analog input module ADC 570 and ADC 970. So that's two different modules. One is a 6-channel, another is a 12-channel. They otherwise have the same specifications. They both support voltage, current, or thermistor as inputs on each of their channels, channel by channel selectable. And the module handles all the linearization and conversion to temperature on board. So you don't have to do any of that externally or in your program. And the values that are reported by the module, the temperature values, are in degrees C or degrees F, and they're reported in 10th degree increments. Now, you can also find thermistor support as a special order I/O option in the XLE and XLT, the XL series, and the XL Prime series. So the Model 2 I/O option is available with either a 2-channel or 4-channel special order option. The Model 3 and Model 4, which have solid-state outputs and slightly different mixes in general, they have a 2-channel option for thermistor. Now, because this was kind of added after the fact as a special order, the linearization and the temperature conversion is handled in the application program. So that's not something that the firmware of the OCS handles automatically. That needs to be handled in your program. But don't worry, we've got a document that fully covers that. I'm covering all the details and demonstrating all the details of how to do that today during our presentation. And we'll also be posting, after the fact, we'll be posting some example programs and even a user-defined function block that can do that for you. Okay, now again, as Casey mentioned in the open, we do have an 8-channel thermistor module coming for OCS-IO later in 2023, so look for that module as well. And that one will also support linearization internally, I'm sure. Okay, now the next thing we're going to talk about is which thermistors are currently supported. Because as I've mentioned a couple times already, thermistors are not standardized like RTDs and thermocouples are. And the resistance versus temperature tables can vary by manufacturer. So at Horner, we've got a couple different brands that have been around for a really long time of thermistor manufacturers that we're supporting, starting with Keel Engineering. Their Precon 10K ohm Type 3 thermistors, we support those. And then from Yellow Springs Instruments, otherwise known as YSI, we've got some 10K thermistors that are also supported, and you can see those part numbers listed there on the chart. So if you're looking to use thermistors with the Horner products, you need to choose from these particular thermistors. Okay, now what about other brands? How could you potentially apply other brands with a Horner product that supports thermistors, such as a XL Series Model 2 special order, for instance? Well, in theory, you could use an equation called the Steinhardt and Hart equation. And if you had that equation and the temperature versus resistance chart for the thermistor you wanted to use, in theory, you could apply a mathematical equation and come up with a resistance to temperature type conversion. However, that is beyond the scope of today's topic, but we might revisit this in the future, and I may even create a user-defined function block to handle all the calculations for you, but we'll see if that happens in the future. Okay, now let's give a little more detail about the process you need to go through when you're linearizing the values that are coming back from your Model 2, Model 3, or Model 4 thermistor option. What do you really need to do as part of the linearization? Well, what you're going to be doing is taking your raw analog input reading coming from the AI channel, and you're going to be running that through an equation. And that equation is complicated enough where it actually takes 2 math expression blocks to execute it, just because of the length of it. Okay. And it also involves a series of coefficients, 8 of which to be exact, which are used in the equation. So we have a document that we've created, Horner document supplement 797, that provides all the details. But getting back to the specifics, what you're going to do is you're going to take the coefficients that we provide you, or the constants we provide you. You're going to use a constant move block to load those into registers if you're using register-based advanced ladder, or variables if you're using variable-based advanced ladder. And then you're going to execute an equation shown at the bottom there that basically takes your raw analog input value, converts it to a real number, runs it through the equation, and then spits out at the end the temperature in real numbers. And again, we've got that document with all the details. Now we're going to jump from our slide content over to our demonstration, and let's get started with that. Okay, so let's start by looking at the bench. Okay, so what do we have here on the bench? Well, I've got a smart block module here. Okay, so this is an ADC 570 smart block. It has 6 channels of analog input, all of which can be configured for a thermistor. And you can select that channel by channel. I've got an XLE with built-in Ethernet. that also includes the XL series with thermistor option. Okay, so this happens to be a Model 2-10, which has 2 channels of thermistor and 2 channels of regular analog. And then I have a EXLW touchscreen OCS, which is just really being used to communicate with the ADC 570 and also to display the values for both the ADC 570 and the XLE. So that's the equipment I'm using here. Oh, and one important note, here is the thermistor sensors, one connected to the ADC and one connected to the XLE. All right, so let's dive into Seascape and take a look at how we set everything up. Okay, so we're going to start out in the EXLW program, and we're going to start by taking a look at the configuration for the smart block. Okay, so here we go. I will pull up the configuration hardware here. All right, so you can see I've got an EXLW, and I'm going to go to the CAN IO tab because Smart Block is a CAN IO family. And I've already added this ADC 570 6-channel analog input module. Let's double click here and take a look at how I've configured it. Okay, I've assigned a CSCAN ID of 1, and I've also assigned the starting real-world analog input register as AI32 as an array. Now I'm using variable-based advanced ladder, so it uses arrays for its real-world analog input values as variables. So AI32 as an array, remember arrays are zero-based, that correlates to %AI33 as a real-world analog input memory register. And there are 6 consecutive analog input values which are going to be reported by the smart block. I've also assigned a status variable, which is always important to monitor the health of any kind of remote I/O block. And then on the 6 channels, for channel number 4 only, I have selected a 10K thermistor as the input. Okay, so you can see here all the different types of inputs that are available. And for channel 4, I've selected a 10K thermistor, and I've opted for degrees Fahrenheit instead of degrees Celsius, and those values will be reported back in 10th degree increments. Okay, so that's the configuration. That's all that's required. It's very straightforward. Now let's take a quick look at the data watch, and we can take a look at the data coming back, the raw data coming back from the smart block. Now again, it's only channel 4 that's configured for thermistor, and that is showing me that we're at 65.9 degrees Fahrenheit for that particular thermistor input because I'm getting an integer value of 659. It also kind of illustrates how AI35 as a real-world I/O array in variable-based advanced ladder correlates to %AI36 when it comes to actual memory addresses. All right, so that is the data coming back from the smart block. And if we take a quick look at the bench, again, we can see right here, there's that data being reported by the smart block at 65.9 degrees Fahrenheit. Now you'll also notice I have here an ADC 570 OK LED or indicator on the screen. How did I create that? Let's talk about that for a minute. Okay, back to Seascape. I'll go ahead and expand the program here and show under the Receive I/O section that I created a single rung that monitors the status register of that smart block. Remember, we assigned a status variable to the smart block. And if it has a value of 0, then we know everything is good. So we can turn on our OK indicator. And if it's off, then later in our program or other places in our program, we can take appropriate action. Okay, so that's what's involved. Not really that much, frankly, in using the ADC 570 or 970 smart block modules for thermistor inputs. Okay, but there's a little bit more involved, as we talked about earlier, in the XL series thermistor option. So let's cover that now in our XLE. All right, so let's start in the main loop there. Okay, and you can see no code there. That's because I want to cover configuration first. So we go back into hardware configuration. This time it's our XLE we're looking at. And instead of looking at CAN I/O, we're going to look at local I/O because this is a built-in I/O option. We'll select Config and then Module Setup, and we'll go to Analog In. Now, what you won't find in the XL Series configuration, for instance, is you won't find as an option Thermistor. That's because Thermistor support was kind of added after the fact as a special order, and it's not handled by firmware, really. So when you're using a Thermistor with the special order XL Series option, you need to select voltage as your input range for any channel that's supporting Thermistor. And since this is a -10 two-channel module, I've opted for voltage on the first two channels. And then for the channels 3 and 4, I would just select those for whatever type of temperature sensor I was using there. But for 1 and 2, those need to be set to voltage if I'm using Thermistor. I also have cranked up a little bit the filter constant all the way to 7. Why have I done that? Well, in a lot of temperature applications, I'm really not that concerned about response time because temperatures are generally going quite slow, especially with thermistors for air temperature and those sorts of things. So a filter constant of 7 gives me a really stable reading, and I value that typically more than super responsive type response. Okay, so that's the configuration of things, but all that does is get a analog input value coming from the module or from the built-in module into my analog input register, but it doesn't linearize or convert to temperature. So how does that accomplish? Well, that's where we talked about that equation that we need to execute to take our analog input reading and convert it to temperature. So here we go with that logic. So what I've done here is I've moved 8 coefficients, okay, that were provided in that thermistor supplement, and I've inserted them into a constant move block, all right, and you can see that they are in scientific notation with 6-digit levels of, I guess, resolution, if you could say. It's not really resolution, I'm using the wrong term there, but I think precision is what I'm looking for. There we go, 6 digits of precision. All right, and since I'm using variable based advanced ladder, I'm copying these values into a variable array that is a real type variable with a dimension of 8. That way it can hold 8 different values from TKF0 through TKF7. And I chose that variable name because I'm having it stand for thermistor constant for Fahrenheit. Now, if I was doing the conversion in degrees Celsius, I could use a different set of coefficients that are geared towards degrees Celsius. And I created a different real array with a dimension of 8 for thermistor constants or coefficients degrees Celsius. Okay, but I'm only going to be using the degrees Fahrenheit in my particular application example here. So I've taken those coefficients, I've taken my raw value that's coming in through my analog input register, I've run it through this calculation, which takes 2 steps because it's pretty lengthy, and then I took an extra step that isn't necessarily required, and that is, at the end of my calculation, I not only have a real value in degrees Fahrenheit for my temperature, but I've also taken and created an integer value in 10th degree increments of that same temperature by taking the real value, multiplying by 10, and then converting from real to an integer. Okay, so that's what I've done in the XLE. Let's take a look at my benchtop here, and you can see here's what we've got. Okay, so the raw value coming in from my AI is about 19,000 counts. And after I've run it through my equation with those coefficients, I end up with 66 degrees Fahrenheit approximately, okay, which correlates to 18.9 degrees Celsius. And I did the Fahrenheit to Celsius conversion elsewhere in ladder to kind of make that happen. Okay, so that's what's involved on the XLE from a channel by channel basis for every channel that you're using thermistor for. Okay, but you'll also notice that I have the XLE's thermistor value being displayed here, as well as an OK indicator as well for that particular controller. So how did I do that? Let's review that real quick. Okay, this would be kind of an extra part of the application that most applications wouldn't need unless you're using the XLE as a remote I/O block hanging off of an OCS. Okay, so we're back to Seascape. And before I cover that how did communication work? There's one more thing I wanted to show you, and that is this. I not only created this example program that I just reviewed with you, but I also created another XLE program that uses a user-defined function block to do the linearization and conversion. And I'm making this available as a download as well. So what this user-defined function block does is you simply name it, because of course you can have multiple instances of this function block if you have multiple channels of thermistors, for instance. The input to the function block is your analog input value directly from your %AI, or in this case, because it's variable base advanced ladder, from the AI0 element of the real world analog input array. So that's where the analog input value is coming from. And then it's going to spit out a real value in both Fahrenheit and Celsius. And I put them both in there for convenience. And if you want to take a quick look at what the code looks like for that user-defined function block, you can see we've got the constant move here with those coefficients for degrees Fahrenheit. And then we're doing the conversion of our raw value, running it through the equation. And then here's our extra step to convert degrees Fahrenheit to degrees Celsius as another output. Okay, so that's what the user-defined function block looks like, and we'll post that so you can download that if you want to use that as an option in your application. Okay, let's get back to how the XLE is actually broadcasting its temperature, its thermistor temperature, over the C-scan network, how that's being received by the EXLW so it can be displayed on the screen and used in the EXLW logic program. Okay, so I'm going to go to the XLE program, to the broadcast IO section of the program that I created, and I'll show you how this works. So effectively, I'm taking advantage of the 100 millisecond timer or tick that's built into the OCS firmware as a system bit. I'm taking that and creating a one-shot that turns on every 100 milliseconds. And every 100 milliseconds, I'm taking my real value from my user-defined function block, which is, obviously in degrees Fahrenheit. I'm multiplying that by 10 to create a new variable that's in 10th degree increments. I'm converting that to an integer and broadcasting it out over CAN. Okay, and when I broadcast it out, the XLE needs to specify its own CAN ID, which is handled by the system variable CAN ID. It's sending the data out as global data, analog global data. It's the first word of up to, I think it's 32 or 64 available AQ values. So the offset is 0. And the source data is that integer value in 10th degree increments that I just created earlier in the rung. Okay. And I'm only sending one word. So it's important to note that you don't want to send or put data to the network every single scan. You want to do it on a periodic basis. So that's why I took advantage of this 100 millisecond built-in timing capability and created a bit that was on once every 100 milliseconds to do the sending. Okay, so that gets the data to the network. How is it received by my EXLW? Well, let's go back to that program. And I've got another section of that program called Receive IO, effectively where I'm using a net get function to retrieve data that was broadcast by network ID 2, which was the XLE. It's coming in from the analog data from the XLE, again with no offset, and I'm copying it locally into this local variable. All right, so that's all that's required there. And then one last thing to show you, and that is this. I've also created an OK bit for my XLE, or the data coming in from my XLE, so that if my XLE stops communicating for more than a second, then I can turn off this coil, which otherwise would be on. Okay, and then if we go take a quick look at our overhead view once again, okay, we can see, sure enough, there's the value coming in from the XLE, 65.9 or 66, and it's reflected here, and there's the OK LED. And if I were to stop this controller, well, let's go ahead and do it now. If I go to the system menu and I go down to status, I could stop the XLE, and therefore it would stop broadcasting the data, okay, within about a second, or just over a second. The OK light went out. And now if I restart the XLE, go back into run mode, you can see very quickly the status went green again. Okay, so that is a look at how to apply Thermistor with the Horner OCS. Okay, so that wraps up all the material I wanted to share with you today. Let's go ahead and do a wrap-up. So the important points today are that thermistors are very popular in building automation applications. They're very inexpensive. They only support a narrow temperature range, but for HVAC and building automation, that's not a problem. And unlike RTDs and thermocouples, it's important to remember that thermistors are not standardized. So be careful in terms of which thermistors you source. If you're using them with a Horner controller, choose from the Kiel or the YSI. Those are widely available, very inexpensive, and they'll work extremely well with the Horner controllers. Okay, next I want to mention that once again, we're celebrating our 10th anniversary with the Horner Lighting Group, and we have an event tomorrow. For those of you watching live, you can join our lighting webinar in about 23 and a half hours, because tomorrow at 2 o'clock, we've got a lighting webinar where we're going to teach you about our hazardous lighting fixtures, and we're going to reveal a special promotion that we've got going in the first quarter of this year. Now, I'm sure Marcy has posted that particular link, that big marker link for the webinar, so you can access it either if you're watching on Big Marker today, or she'll have it posted in the comment section if you're watching on YouTube. Okay, next week, we've got a great program for you. We're going to talk about installing a Horner OCS outdoors using a new accessory from Stalin. Stalin is an enclosure manufacturer, and they've got a product called a solar shield. And that solar shield is useful in any outdoor application where you're using a touchscreen and you're interested in shielding the sun while you're using the touchscreen, and also protecting the touchscreen from the effects of UV while it's out and generally not in use. While this is not an absolute requirement for an outdoor application, it's a terrific option, and we're going to have the product line manager from Stalin join us next week for our program. For those of you who have not yet subscribed to our channel, I'd encourage you to do so. It doesn't cost anything. And if you choose to subscribe and you choose notifications, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, let's all get out there and do us some good.